And hello, everyone. Thank you for joining us for our webinar today. Today, we're going to be talking about post-quantum cryptography, and we'll be going into an overview of post-quantum crypto, looking at some of the activities that NIST is doing as part of that post-quantum cryptography standardization process. And then we'll take a look at what wolfSSL is doing internally and what we're thinking about adding in the future as far as post-quantum support. Yoko mentioned my name is Chris Conlon. I'm an engineering manager at wolfSSL. I'm based in Bozeman, Montana. And hopefully at the end of this, we're going to have some time for question and answers for you to ask us if you're interested in any post-quantum support that wolfSSL can help bring to the market. So let's start out with a quick overview of wolfSSL. So we focus on three main things: data at rest, secured with cryptography and WolfCrypt, securing data in transit with SSL, TLS, and SSH, and then securing firmware updates by mixing secure transport together with secure boot. Working on SSL and TLS and cryptography, that's a very horizontal technology, and so we end up going into a lot of different vertical markets. Some of the types of customer markets that we have customers in currently are shown on this slide. So, everything from appliances to IoT devices to applications or printers or automotive. These are all examples of industries secured by wolfSSL. wolfSSL started in 2004 out of the MySQL database. At the time, MySQL needed a clean room SSL implementation, and our co-founders wrote our first SSL library to meet that requirement. So our first library was called YASL, which stood for yet another SSL. It was written in C++. And after we wrote YASL, the market really was asking us for a C library instead of a C++ one. We rewrote it again from scratch in C this time and called that CYASL. And then in 2014, we renamed that to wolfSSL just to be more consistent across product naming and fit our company culture a little better. And so wolfSSL is now our main product today. wolfSSL has had some exciting company growth since we were founded and started to grow the company about 10 or 11 years ago. Now we have over 1,000 commercial customers that are using wolfSSL products, 17 resale partners. And our best estimate is that we secure somewhere around 2 billion active connections at any one time on the internet. We do have a pretty broad partner program that we work with a lot of the silicon vendors, operating system vendors, RTOS vendors. And our goal here is to make sure that wolfSSL products run on these platforms out of the box so our customers can get up and running more quickly. So here you might see some familiar names. This is our current product lineup on this slide. So our main product is wolfSSL, our SSL and TLS library. WolfCrypt is our cryptography library that sits underneath wolfSSL. We have a couple of validated or certified versions of WolfCrypt available, one FIPS 140-2 for government DoD projects, and a DO 178 certification for avionics. We have an MQTT client, SSH client and server, a TPM 2.0 library, and a secure bootloader called wolfboot. And all of those primary products are written in C. We do have users that want to use us from other languages. And so we have wrappers for Java, C#, Python, and JavaScript. And in the third row is a set of applications that we have available. We have an SSL termination proxy, a simple certificate enrollment protocol, a secure update solution, a command line utility. And we now have the author of curl, Daniel Stenberg, as a wolfSSL engineer. So we offer commercial support for curl, as well as consulting services, supporting curl to new platforms, adding new feature additions. And we have a version of curl that's meant for resource-constrained devices, which we call TinyCurl. All of our products are dual licensed under a commercial license and an open source GPL v2 or v3 license. I mentioned wolfSSL is our main product, so we support up to the most current protocol standards today of TLS 1.3 and DTLS 1.2. Footprint size for wolfSSL ranges between 20 and 100 kilobytes, depending on build options and compiler. Runtime memory is 1 to 36 kilobytes. And we've ported to most of the operating systems and RTOSs that we've encountered so far. So we support 30 to 40 different operating environments now. A lot of the operating systems and RTOSs are listed here on the bottom of this slide. Some other features of wolfSSL include an OpenSSL compatibility layer. This makes it easier for applications to migrate from using OpenSSL over to wolfSSL. We've ported into a number of different web servers, including Apache, Nginx, Lydie, and Mongoose. A big differentiator for wolfSSL is the ability to take advantage of hardware cryptography. So if this is available in your silicon, oftentimes we can offload to the hardware crypto instead of using our software cryptography. This will give you performance increases as well as code size reduction. wolfSSL is NSA Suite B compatible and also has our validated and certified versions available. An exciting thing for us in the last couple of years has been TLS 1.3. And so we're proud that we can bring that to the market, and that's available today in wolfSSL. Some advantages to TLS 1.3 is it's more secure with old algorithms removed and also better performant by requiring one fewer round trip during the handshake process. So if you want to learn more about TLS 1.3, I'd direct you towards our webpage at wolfSSL.com/TLS13. Being a security product, testing is one of the most important things for us. So we're always adding more testing to our test environment, adding more platforms and different types of testing. Here you can see different types of testing that we're currently doing. So everything from API unit testing through CypherSuite algorithm benchmark testing. We do static analysis with tools like Coverity, ScanBuild, and Facebook Infer. We do dynamic memory testing with Valgrind and Clang's fsanitize address, interop testing against other major implementations. We test real world builds where we're building our customers' builds on a nightly basis, testing with different compilers. Every line of code that makes it into wolfSSL products is peer reviewed. We also have third-party testing through either security groups of our customers or through academic or research institutions. And we do a bunch of fuzz testing with over 6 different fuzz testers. And then we wrap all this up into a continuous integration cycle using Jenkins on our backend system. wolfSSL is available from the wolfSSL.com website or directly from GitHub if you want to follow our development progress. So now let's move into talking about post-quantum crypto. Here you can see a post-quantum computer that was from the IBM Q System 1 computer shown at the Computer Consumer Electronics Show in 2020. And so for those of you unfamiliar with quantum computers, we're going to start out kind of at the basic level here at just what is a quantum computer. And so this is a computer that uses quantum phenomena, so superposition, entanglement, to perform the computations. A quantum computer uses a qubit instead of a traditional bit, where classic computer bits are either a 0 or a 1. A qubit can be a 0 or 1 or a superposition state between 0 and 1. And now that we know, what is a quantum computer, why are they posing a risk to classic cryptography? And so the answer here that we're looking to find is Shor's algorithm. And so this was invented by Peter Shor in 1994. And it's a polynomial time quantum algorithm for integer factorization. So if you think of your math classes where you given an integer n, you find its prime factors, that's essentially what Shor's algorithm is doing. And it demonstrates that the integer factorization problem can be efficiently solved on a quantum computer. And not only that, but it's exponentially faster than a classical factoring algorithm. So what this means for us is that, a lot of our algorithms and public key algorithms, especially today, are going to be broken with the advent of a powerful enough quantum computer. Our current public key algorithms today rely on one of these hard problems to maintain the security of the algorithm. So either the integer factorization problem, the discrete logarithm problem, or the elliptic curve discrete logarithm problem. And quantum computers, there's a lot of resources going into development of quantum computers. And so the general sense is that it's only a matter of time before there's one kind of powerful enough to break these algorithms. So that brings into the picture post-quantum cryptography. So post-quantum crypto is also referred to as quantum proof, quantum safe, or quantum resistant. And these are algorithms designed to be secure against an attack by a quantum computer. Some of the goals of post-quantum crypto include the development of crypto systems that are secure against not only a quantum computer, but also a classical computer, and also the development of systems that can interoperate with existing communication protocols and networks. So we want to make sure they still work with SSL and TLS, IPsec, and the other protocols that applications and consumers are using today. So in the US, NIST is working to help find a solution to this problem. NIST is the National Institute of Standards and Technology, and there's also several bodies around the world that are working with them in this process. So in 2016, NIST began what they call the post-quantum cryptography standardization process. And they began this for kind of two main reasons that they called out in their call for papers. And so the first reason was that they noticed there'd been noticeable progress in the development of quantum computers. And here I have a couple of quotes taken from their call for papers in 2016. And so for this one, they stated theoretical techniques for quantum error correction and fault-tolerant quantum computation, and experimental demonstrations of physical qubits and entangling operation in architectures that have the potential to scale up to larger systems. So they're saying they're seeing more effort go into the development of quantum computers, and they're foreseeing that we'll have a powerful enough quantum computer sometime in the near future. The second reason is that they realize that the transition to post-quantum crypto is not going to be simple, meaning that having the industry switch over to post-quantum algorithms is going to take time, and it's going to take a significant amount of effort and time to do that. And so the sooner that we start searching for a solution, the more time there is to switch over to a post-quantum algorithm configuration. So the new algorithms that come out of the standardization process will be quantum resistant counterparts to the existing standards that NIST has. So this will be NIST FIPS 186 for digital signature schemes, and the special publication 800-56A, and B for key establishment. So in one of the NIST reports, the NIST IR 8105, which was a report on post-quantum cryptography, they had this table in that report. And this is essentially the impact they see quantum computers having on our traditional crypto algorithms today. And so in the first column, we have the cryptographic algorithm. The second column is the type of algorithm that is. The third column is that algorithm's purpose. And the fourth column is the impact that a quantum computer will have on that algorithm being secure. So if we look at, say, AES, for example, so this is a bulk encryption algorithm. It's a symmetric key algorithm used for encryption. Here, fortunately, symmetric key algorithms they're expected to be secure in a post-quantum world. The only thing that will be needed here is applications will need to use larger key sizes. SHA-2 and SHA-3 are going to need to use larger digest sizes. But then as you can see, RSA, ECDSA, ECDH, and DSA will all be considered no longer secure. So if you look on the NIST post-quantum website, this is the timeline for their standardization process. So they started their call for proposals in 2016. They've gone through 3 rounds of algorithms so far. So the round 1 algorithms were announced in 2017. Round 2 were announced in 2019, round 3 in 2020. And the process is projected to finalize in 2022 or 2024. So here's the kind of the progression of these rounds in numbers of algorithms that were in each round. So they started with 69 submissions. By round 2, they had evaluated the forerunners of those submissions and narrowed it down to 26 algorithms. And round 3 took that a step further with a total of 15 algorithms. So here we can see all the algorithms that were listed as part of the round 1 submission. There were 69 in total, and this was on December 21st of 2017. By January of 2019, the round 2 candidates were announced, and you can see that that cut the list down quite a bit, down to 26 algorithms, and also split them out between public key encryption and key establishment and digital signature algorithms. And then round 3, on July 22nd of 2020, the finalists for the round 3 candidates, it was split between finalists and alternate algorithms. So if we look at the round 3 finalists for public key encryption and key establishment, they have classic McKellis, the Crystals, Kyber, Entrue, and Sabre algorithms. You can see that 3 of these are lattice-based, and one of them is a code-based algorithm. And what NIST is saying is that they're most likely to only pick one lattice-based algorithm per algorithm category. So one of the Crystals, Kyber, Entrue, and Sabre is expected to be chosen as one of the forerunner finalists. And then here's the finalists from round 3 for digital signature algorithms. So the Crystals, Dilithium, Falcon, and Rainbow. Again, here the first 2 are lattice-based, and the third one is multivariate. And then along with those finalists, NIST has chosen these alternate candidates from the round 3 submission process. And so they're not excluding these alternate candidates. They're saying that some of these could potentially reach standardization as part of a 4th round, but they'll need more analysis put in before that point. So if you're interested in reading more on the round 2 evaluation process, there's a very detailed NIST document that goes into their thoughts on each of those algorithms. This is the NIST IR 8309 document. So we put a link here for your reference on that. So now that we've talked about, what is NIST doing, now you're probably wondering, what is wolfSSL doing in relation to post-quantum cryptography? So if we look back, wolfSSL has actually been working with post-quantum cryptography since 2010. So we'd originally back in 2010 saw this as something that people were going to start to be interested in. And so we partnered with a company called Security Innovation to bring the experimental Entrue algorithm support to wolfSSL. Entrue stands for the nth degree truncated polynomial ring units. That's where the acronym comes from. This is a lattice-based scheme that was originally separated between Entrue encrypt and Entrue sign. It's one of the oldest post-quantum lattice crypto systems, old enough that all the patents for this algorithm have now expired, and it was placed into the public domain in 2017. And just for reference, the public key sizes for Entrue range between 699 and 1,230 bytes. One of the things that people will consider when looking at these post-quantum algorithms is the key lengths of these algorithms. Some of them get to be quite large. And then following the Entrue addition to wolfSSL, we took this support one step further in 2015. We added support for the QSH, or Quantum Safe Hybrid Handshake extension. And so this is an extension that allowed an existing TLS cipher suite to become quantum safe and make the traffic in that connection essentially safe from someone who would record it and then later try to decode it or decrypt it with a quantum computer. So this also uses Entrue with a one-time Entrue key to encrypt some extra secret material. If you're interested in learning more about QSH, we've linked the draft specification here on this slide. So when you're building wolfSSL with ntrue or QSH support, there's a with ntrue option. So -- with ntrue for configure. For QSH, you also, in addition to the with ntrue, need to use the enable QSH build option. Now going forward, this year, so every year wolfSSL sits down and puts together our roadmap for what we want to focus on in 2021. And one of the things on our roadmap this year is to start implementing some of the NIST round 3 candidates into wolfCrypt and will be usable from wolfSSL, hopefully the SSL and TLS level. And so this will allow wolfSSL users and customers to start to adopt these early, to start prototyping and testing with post-quantum algorithms. For our algorithm selection process, it's going to depend on a couple things. We'll want to make sure the algorithms we choose are easy to use with TLS. We'll want to stay conscious of the key sizes, since some of them have rather large key sizes. And then maybe more importantly than anything is depending on what our customers and users are interested in using as far as algorithms go. So if you're interested in using a specific round 3 candidate algorithm, please let us know, and that can help us prioritize the order that we implement these into wolfSSL. One other thing we're considering adding support for is the liboqs library. This is open quantum safe. It's an open source library that implements a lot of these post-quantum algorithms. So wolfSSL could add support for the liboqs API, and our users would automatically kind of gain access to all the algorithms in open quantum safe. Just for reference, these are all the key encapsulation mechanisms supported by liboqs. And here on this slide are all the signature schemes. So with that, hopefully that gives you some insight into what we're looking at wolfSSL and kind of where the post-quantum crypto standardization process is at as far as the NIST competition and process is going. So I'd like to open it up for any questions you might have, or we appreciate any feedback you might have on if you're interested in post-quantum algorithms, or which algorithms you might be interested in using in wolfSSL.
ご質問がありましたら、英語で Q&A ボックスの方へご記入いただければと思います。今、日本語で一つご質問いただいておりますのが、この資料は配布していただけますかということですが、後でご参加者の方には、資料の方をご連絡させていただきます。配布いたします。で他に来ている英語の質問ですけれども、What is timeline for adding post-quantum algorithms to wolfSSL?
Yeah, so it's a good question. And our timeline for adding algorithms to wolfSSL is, our goal is to add them in 2021. But if we're hearing interest from users or customers, that might be accelerated.
Thank you. And next question is, how much does the performance of embedded devices decrease when ntrue is enabled?
So yeah, that's a good question too. The performance of ntrue in wolfSSL. I don't have that number off the top of my head, but we have integrated that into our wolfCrypt and wolfSSL benchmark applications. And so that would make it easy to build that on a given system and run the benchmarks to see. I think we've also posted that in a couple blog posts, at least on our wolfSSL.com blog. So that would be a good place to go back and reference that information.
Next question is, are there any customers who actually use ntrue or QSH in their products?
So for customers that are using ntrue or QSH, we don't have any commercial customers that are using that combination yet. we originally added that as kind of an experimental support to gauge interest. And we have had several people interested in using it and trying it and testing it, and also some academic researchers that have looked at it. But yet, as of yet, we haven't seen that adopted into any commercial products yet.
Thank you, Chris.